Nuclei are bound together by the strong forces. This force is about 100 times greater than the electric force between two protons. Both protons and neutrons are affected by the strong force. The strong force is what binds protons and neutrons together in a nucleus. The strong force is short-range force. Because protons and neutrons appear to act identically to the strong force, even though the proton is electrically charged, they are often considered interchangeable and are called nucleons or nuclear constituents. Only when the distinction is important we call them protons or neutrons. The reason for this is protons repel each other by what force and tend to make nuclei unstable. The neutrons act to screen the protons from each other, making the nucleus stable. For effective screening, there needs to be more neutrons than protons. When protons and neutrons react together, making bonds, they give up energy, nuclear binding energy. The binding energy increases as protons number increase. The binding energy must increase with the number of nucleons, because to get more together, they must collectively give up a large amount of energy. The differences between fission and fusion. The main differences that there is between fission and fusion is that fission is splitting of an atom to form two smaller ones, while fusion is the fusing of two smaller atoms to form a larger atom. In each of these, the binding energy of the final products is higher than that of the prerequisites. This is explained more fully in the next section. Fission itself is a nuclear process which does not usually occur naturally in nature, at least not that we know of, as it requires a large mass and incident neutron to start the reaction. However, this will not last for a long time, as the reaction will explode and produce a result such as an atomic bomb. This volatile nature is what prevents fission from occurring for any length of time naturally. Fusion, on the other hand, is a process which occurs quite naturally. In fact, if fusion did not occur naturally, we would not be around today. This is due to stars being the result of the fusion process, the fusion of mainly light atoms into heavier atoms. Fusion also releases a lot more energy in comparison to fission in relation to the mass input. Put it simply, you will get more energy released from the fusion of 1 kilogram of hydrogen ions than you will from fusion of 1 kilogram of uranium. In nuclear fusion, the nuclei of atoms fuse together, causing much more energy being released than in nuclear fission. This is the process which powers the sun. Here, the deuterium and the tritium atoms, these are the isotopes of hydrogen. These have extra neutrons in the nucleus than normal, fuse together to form He. Energy is released due to a difference in mass between He atoms compared with the sum of the hydrogen atoms. Therefore, it is conclusive evidence that some mass is converted into energy via Einstein's relationship of E equals mc squared, where E energy and m mass of nuclei and c speed of light. This is why the energy E release is greater than the fusion of the fusion, because of a very large mass deficit. When a nucleus fission it splits into several smaller fragments. These fragments, or fusion products, are about equal to half the original mass. 2 or 3 neutrons are also emitted. Nuclear fission, the sum of the masses of these fragments, is less than the original mass. This missing mass, about 0.1% of the original mass, has been converted into energy according to Einstein's equation. Fission can occur when a nucleus of a heavy atom captures a neutron, or it can happen spontaneously.